Let's talk about text embedding. This is where things get really interesting. Embeddings are like the secret language that machines use to understand words. Instead of just representing words as they appear, embeddings transform them into continuous vectors in a high-dimensional space. Think of it as creating a map where each word is a point, and the distance between these points reflects how related the words are. For example, words like dog and puppy would be mapped close together because they have similar meanings. This transformation allows the model to understand not just what the words are, but how they relate to each other. The vector you see on the right is how a phrase might be represented, as a string of numbers in this semantic space. Let's have a visualization of semantic similarity. Imagine each dot in this 3D space represents a word or a concept, and their positions are based on how similar they are in meaning. Notice how words or concepts from the same category, like animals, athletes, or transportation, are grouped together. This shows how embeddings help us understand relationships between words. For example, we can see that the words related to transportation are clustered here in blue, while athletes in green forms a different group. The idea here is the closer the points are in this space, the more related or similar the meanings of the words are. Now think about how this helps model. When it's trying to figure out the meaning behind a query, it can look at where words fall in this space and understand their relationships, even if they are not exactly the same. So what we are seeing is how embeddings can represent meaning, not just individual words, but as clusters of related ideas. Now that we have seen how words are positioned in a similarity space, let's look at how the model creates this space. On the surface, we see the model generating text, but behind the scenes, the process starts by converting the input text into embeddings, which is a numeric vector that represents the meaning of the words. Instead of working directly with text, the model uses these vectors to understand the relationships between words. These embeddings allow the model to navigate that similarity space we talked about, helping it understand context and meaning. So while we see text generation, it all starts with text representation, converting words into something the model can truly work with. We are looking at word-to-vec, a technique that transforms words into vector representations. Let's take a closer look at the examples. On the left, we have three words, kin, man, and woman. Word2vec takes these words and represents them as vectors, shown on the right as a combination of colored blocks. Each block represents a specific dimension in a high-dimensional space, and the color patterns illustrate the relationships between the words. What's interesting is that words with similar meanings or relationships, like man and woman, have vectors that are close together in this space. This allows the models to understand relationships between words. So word2vec helps the model capture these semantic relationships and use them to better understand the meaning behind words and how they relate to each other in various contexts. Let's zoom in on what those vectors actually look like. Here, we have the word embedding, or kin. You can see it's just a series of numbers. These numbers represent different dimensions, each capturing some aspect of the word's meaning. To make this easier to understand, we can color code these values, as shown at the bottom. The colors represent the magnitude of the values. Reds for higher positive numbers and blues for lower negative ones. Let's expand that idea to a whole list of examples. Here you can see the word embeddings for different words like woman, man, king, and queen, displayed as colored blocks. Each row represents a word, and each column shows a dimension of its vector. Notice how the colors vary across words. What's interesting is that words with similar meanings, like man and woman, or king and queen, have similar patterns in their vectors. These patterns are what help models understand relationships between words, even when the exact word doesn't appear in a query. Let's look at these interesting analogies. Here is a famous example. We can actually calculate this relationship using word embeddings. If we take the embedding for kin, subtract the embedding for man, and add the embedding for woman, we should end up with something very close to the embedding for queen. This is possible because embeddings capture not just the meaning of individual words, but also the relationships between them. On the right, you can see how these word vectors align, showing how this analogy works in the model's internal representation. So embedding allows us to perform these kinds of operations, helping the model understand more than just words, but also how they relate to one another in context. Now that we have seen how individual words can be represented as embeddings, let's take it one step further and look at sentence embeddings. Here, entire sentences are transformed into vectors, just like we did with individual words. Each row represents a different sentence, and each column is a dimension of its embedding. This allows the model to understand the context and the meaning of full sentences, so that we can compare or relate them based on their underlying structure and content. Similar as words, let's see how sentences can get organized in semantic space. Here we have different sentences placed on a two-dimensional grid. Each dot represents a sentence, and similar sentences are grouped together based on their meaning. For example, sentences about ground transportation are clustered on the right, while those about airline tickets are on the left. In the middle, you can see queries about airlines. This visualization shows how the model places sentences in a meaningful space, where similar ideas are close to one another. This is how embeddings allow the model to understand not just words or sentences, but the relationships between different concepts. We've talked about how embeddings convert words and sentences into vectors that represent their meaning. This allowed the system to compare semantic similarities rather than just matching keywords. But the real challenge emerges when we have long documents. How do embeddings help us find the right information in massive amount of text? There is a famous experiment to discuss this question. The experiment is called needle in a haystack, and the goal is to retrieve specific information buried deep within long documents. Embeddings play a critical role in navigating that complexity. The basic idea is to see how we can use embeddings to help us find specific information, which we call the needle, in a long text document, which we call the haystack. Imagine I take this sentence, the best thing to do in San Francisco is, and embed it into a long document with thousands of words. The sentence we are looking at in yellow is our needle. We ask the large language model to retrieve the information for the question, what are the best things to do in San Francisco? The system then has to navigate through all the content and focus on where that needle has been embedded. If embeddings are working well, the system should be able to find the correct information and provide a relevant answer. In this experiment, we will change the position of the needle from the beginning to the end of the document. We also change the length of the document. So the research question is, Can the large language model still retrieve the needle accurately as we increase the length of the document and as we put the needle in different positions of the document? Let's see how this plays out with GPT-4. As shorter length, GPT-4 does a great job because the embedding space is easier to navigate. But as the context window increases, we see a noticeable decrease in accuracy, especially when the needle is positioned at 10% and 50% of the document. This suggests that while embeddings help find the needle, the accuracy of retrieval changes depending on where the needle is and the length of the document. Now let's compare with Claude 2.1. Claude has claimed that one of its strengths is the ability to deal with long text more effectively than other models. We ran the same test. While embedding allowed Claude to maintain decent accuracy in shorter context, as we move to longer documents, we see a clear drop in performance. The red areas represent retrieval failures. As we move toward longer text, the red dominates. These findings are super interesting, as Claude has claimed to have superior capabilities to deal with long text. It does not seem to perform so well in this test. What's more interesting is that with the above shocking results, the developers of Claude cannot keep silent. They rerun the experiment and provided an explanation. They said that the problem wasn't with Claude's ability to process long text per se, but rather with how the prompt was framed. In the original test, the system struggled to find the needle accurately. But with a revised prompt, things changed. If we include "here is the most relevant sentence in the context" into our prompt, Claude's performance improved dramatically. This example also highlights the importance of prompt engineering in evaluating the embedding setups of large language models. Let's move into positional encoding. While embeddings provide rich contextual information and represent the meaning of words, they don't give us the sequence or order of the words in a sentence. This is where positional encoding comes in. Positional encoding is all about the sequence. It is a key element described in the transformer architecture, which is central to the large language models like GPT. We talked about this architecture earlier in the course, as well as this very important paper, "Attention is All You Need." Well, we don't need to dive into all the technical details. It is important to focus on how positional encoding works alongside embeddings within the transformer. Let's start with encoder. The encoder takes text and converts the text into a numerical matrix, which is the embedding vector. Then we introduced positional encoding to inject information about the positions of each word in a sequence. In other words, we have embeddings to capture the meaning and positional encoding to capture the sequence. For example, the sentence, "the dog barked at the tree," gets processed. The model doesn't just know the meaning of the words dog and tree through embeddings, but also knows the order through positional encoding, that the dog barked at the tree, not the other way around.